Hi, everyone. So welcome to the webinar. It's right on the time at 3 p.m. Eastern, so we'll get started right away. So thank you all for joining. This is the HEU GeoHealth Early Career Webinar focused on the art of science in communication. So we are really excited to have 3 winners of our elevator pitch competition. If you've seen the sort of 3-minute thesis competition, it's closely aligned with that. So we have 3 winners who you'll hear from today, the presentations. We'll do a little bit of a Q&A. And first, before we get started, I'm just going to go over some housekeeping items. So thank you for joining us. Each presenter will present, upwards of 15-ish minutes. And then we'll have time for questions following each winner's presentation. You can type your questions in the chat, or you can just unmute yourself at the time that we have the question answer. Your audio and video we turned off by default just to save some of the bandwidth. And then if you want to consider joining other talks like this in the future, I'll put in a link to a Google form so you can sign up for more. And then last but not least, since we are affiliated with the American Geophysical Union, AGU, you can join and be part of the great community. We're focused on geohealth, but there's so many other sections that really have a home for everyone. So with that, we're going to start with our first winner, Dr. Yunyao Li, and I will hand it over the reins to them now. So thanks.
Hi, I'm Yunyao. This is my slides. Can you see my slides? Good? Good, okay. Okay, hi, good afternoon, everyone. I'm Yunyao Li. I'm a research scientist from the George Mason University. Today, I want to share with you the progress and insights from our work on the hazardous air quality ensemble forecast system. So as we know, air pollution resulting from natural hazards like wildfires, dust storms, and volcanic eruptions have profound effects on air quality, public health, and climate. These events can transport the pollutions across a vast distance, impacting areas thousands of miles away. Here I showed VIA's AOD observation on September 15, 2020. On this plot, we see that the fire smoke from the West Coast can transport to the United East Coast and affect the air quality and health there. The Earth's warming and the increasing risk of droughts have led to a rise in extreme weather events. Here I show 2 figures. The 2 figures shows an increasing tendency in both fire-burn area and the number of dust storms from the 1980s to the 2020s. Recognizing the significance of these events, air quality forecasting becomes a key tool to inform and help health managers migrate and these damages caused by these events. However, substantial uncertainties persists. Here I show a figure of the PM2.5 concentration from different forecasts, 5 different forecasts, including the NOAA GFS model, the NASA GEOS5 model, the NOAA HERS smoke, the Naval Research Laboratory NAMS model, and the NOAA NAQFC. We see the divergence in the PM2.5 forecast, which proves the forecast uncertainty. These uncertainties arise from various sources, such as the emissions of the dust or fire, the plume height, or the physics schemes used in the model. Here I show the figure displays the PM2.5 total emission from 11 widely used fire emission dataset for the 2020 wildfire season. These 11 products underline a 10-fold differences, and these large differences show us the great emission uncertainty. So how to solve this problem? In response to these challenges, we have developed a Halodex air quality ensemble system. We call it HECAS. It is a real-time multimodal ensemble air quality forecast system, and the system incorporates 5 models from 3 U.S. government agencies, including the NASA GEOS 5 model, the NIL NAMS model, the NOAA HERT smoke, the NOAA GFS model, and the NOAA NAQFC. We include both regional model and global model. And these 5 models use different fire emissions, different plume rise, and different resolutions. So the ensemble diversity is very good. And the HECAS system offers several forecast products, including 3-hourly ensemble mean of PM2.5, black carbon, organic carbon, and AOD. We also have a product called a PM2.5 exceedance probability. It's very helpful for the decision makers. And these products can be downloaded from the NASA Earth Data website. And we also provide daily forecast plots on our GMU Air Quality Group website. Here you can see, let me use a laser. You can see this website. And when you open the website, you can see the daily forecast and you can zoom in, zoom out. It's an interactive data set. And for the forecast, when you download the data, we have 3 formats. The first one is on our model grid. We also provide the data on the county level and the census tract level for the benefit of the health study scientist. Here's the evaluation for our HECAS model. On the left, the figure shows the annual mean HECAS surface PM2.5 concentration compared to the AirNow observation for the year 2022. Our model result matches the AirNow observation. And on the right, the figure shows the model error of HECAS in contrast to the 5 individual models. The black line shows the model error for the HECAS, and you see the black line is the lowest one among all the model results. So that means that our ensemble forecast reduce the model error. And why it can reduce the model error? Here I show the histogram of the model error for all the 5 models and the ensemble mean. And the result, I calculate the result in 6 different United States major fire regions. The region 4 is in the Southeast United States. The region 6 to 8 is in the Central United States, and the region 9 to 10 is in the West Coast. We see that each model has its systematic errors. Like some model always tend to underestimate, and some model tend to overestimate. And the ensemble mean, the HECAS model, balance most of the systematic errors. However, it cannot balance all the models. How to solve this problem? Okay, so to solve this problem, we introduce a weighted ensemble approach. So for the weighted ensemble, it means we will calculate a model weight for each individual model. And we tried 4 methods to calculate the weight. The first method is use multilinear regression to calculate weight. But however, the multilinear regression sometimes has an overfitting problem. So we tried a second method called ridge regression. And the ridge regression add a penalty term to the multilinear regression formula. And the penalty term can reduce the overfitting problem. And we also test another 2 I will introduce later. So here I show the results and compare the original ensemble mean with the 2 weighted ensemble. One is the multilinear regression, and the one use the ridge regression. In this figure, I compare the forecast with the observation. The x-axis shows the observation and the y-axis shows the forecast. So for a very good forecast, the result should be very close to the central line. And the green dots shows the result for the ensemble mean, and the pink dots shows the result for the multilinear regression, and black dots show the result for the ridge regression. We use 3 metrics to evaluate the model performance. The first one is the model bias, and the second one is hit rate. The hit rate illustrates the match between the observation and the forecast for the extremely events. Another one is called false alarm rate. The false alarm rates illustrate the false alarm or the overestimate of the forecast. Compare these numbers, we find that the weighted ensemble reduce the model bias by 40% and increase the hit rate, the match between the observation and the forecast, by 17%, and reduce the false alarm rate by 72% compared to the ensemble mean. So we can conclude that the weighted ensemble overperforms the unweighted ensemble. However, we still see some underestimate. The multilinear regression and ridge regression, also the ensemble mean, all tend to underestimate the PM205 exceedance events. So to solve this problem, we test another 2 weight calculation method. The first one is the quantile regression. The quantile regression calculates a quantile dependent regression coefficient. Here we use a quantile 90% to give more credit to the top of the events. This is a very similar figure. I compare the air now with our forecast. And right now the black dots shows the result for the quantile regressions. And here the table, we show the 3 metrics. And compared to the ensemble mean and the multilinear regression, the quantile regression enables the ensemble model to predict more PM205 high events, but sometimes it overestimates. And the quantile have a much higher hit ratio, and is about 50% higher than the ensemble mean and 33% higher than the multilinear regression. But we also see the false alarm ratio is also high. So we test the last method, the weighted regression. The weighted regression increases the impact of the extreme events in the regression analysis. And we gave a weight of 10 for the high PM205 concentration cases that is higher than 20 microgram per cubic meter. And here's the results. And this is the conclusion. I list the conclusion here. So the weighted regression enables the ensemble model to predict more PM205, high PM205 events. We see high values here and a higher hit ratio. The hit ratio is higher than the ensemble mean and the multilinear regression. And its false alarm ratio is not that high than the quantile regression, which is really good. So we don't have much false alarm. And here's the conclusion. So the natural hazards have a huge air quality impact and health impact, and there are great uncertainties in the hazardous air quality forecast. And here we build a system, the ensemble system called the hazardous air quality forecast HAQUS system, and it reduces the wildfire air quality forecast uncertainties. And we test the weighted ensemble method and find that it works better than the unweighted ensemble. And the 2 methods we used, the quantile regression and the weighted regression, also helps with the forecast of the extreme cases. Thank you. And our study is supported by NASA and HAQUS program and the NOAA WPO. Thank you.
Fantastic. Thank you so much for that awesome presentation. So now I'll invite anyone, if you have any questions, feel free to type them in the chat. You can also just unmute yourself and you can ask your question. I know I have a few, but I'll let other people jump in first.
I have one question. Can I ask? Actually, I saw that your model is for different parts of America, United States. So the results were somehow maybe different in different locations. Was it meaningful? For example, why this place is different from that place?
Oh, yeah. Do I mute? Unmute? Okay. Yeah, yes. So this I think is on this slide. Let me share my screen again. Though this region is defined by US EPA. For different regions, it have different emission source. For example, in the eastern coast, maybe the anthropogenic emissions is higher than the wildfire or fire forecast. And in the west coast, maybe it has more fires. And maybe in the south part, like in the Texas and the New Mexico, there are more dust. So that's why the EPA designed the region like this. And we calculate the model error in different regions. That's because different model have different emissions combinations. And so it's more reasonable to look at different regions. Yeah.
Thank you.
Anybody else have any questions? I'll ask one. I think one of the most like impactful parts of your presentation was that you had so many different types of visuals. Like you had static graphs, and then I saw that you also had that online portal. Do you have any challenges when creating static graphics versus like a web application? Because I've never done anything like that, and I have hard enough time creating scatter plots. So was there any challenges when you're trying to go between the different types of graphics?
Yes. So you see the plots, I use different software to do the plots. For example, the map plots, I use NCL, and the histogram plots, I use MATLAB. I think different software may be good at different different plots. And for the online website, actually, we asked a CS student to help us to build a website. So it's because I work in the universities, there are students from different departments, so we work together to build a website.
Thank you so much for sharing. All right, do last call for questions, but then I'll ask Miriam to queue up afterwards. All right, thank you so much, Dr. Lee. And we'll transition now to Miriam. So let you have the floor, share your slides. You can introduce yourself as well.
Yeah, hello everyone. First of all, the previous slides and presentation was perfect. I forgot to say that, but yeah, let me share my screen. So I guess you see my screen, right?
Looks good.
Okay. Again, hello everyone. Good to see you all here. I'm Miriam Pahtehi, PhD student in civil engineering at FSU University, and my presentation is about the intersection of hurricanes and the human respiratory health. Okay. We all know the visible aftermath of hurricanes, which are evacuation, destruction, and tragic losses. However, among these impacts lies a less understood danger, the profound impact on human respiratory health. Hurricanes bring more than just destructions. They, in fact, leave behind some lingering threats like water intrusion, persistent moisture, and damp environments. These unseen elements pose a significant risk to respiratory health, often leading to conditions like asthma. Despite this risk, there is a critical gap in our understanding. What precisely triggers this respiratory disease after a hurricane? Identifying these factors is important in safeguarding public health in the aftermath. Our NSF-funded research goes deep through multiple potential factors to understand how hurricanes can affect our birthing. Our study began with Hurricane Ida, a severe storm in 2021. It's mainly head north. It mainly head west, south, central, like New Orleans, and then goes up to northeastern New York City and Philadelphia. And then we expanded the study to also include the impact of Hurricane Ian, which happened in 2022. Hurricane Ian mostly hit the southern part of Florida, like Fort Myers, Miami, and Orlando. Both these hurricanes left a trail of major destruction and damages marked by extreme flooding. In this presentation, I will go through these steps. So first, I will explain our survey questionnaires. I'll start by talking about the questions we asked in our surveys. Simple questions, but big in size, how hurricanes affect different homes and people's health. And next, I'll take a look at how homes were inspected. What did we look for and what did we find? Once we collect the sample, it was time for the lab analysis. What information did we get from those samples? And I'll also explain a little bit about our flood modeling work, a quick glimpse into how we simulate and predict flooding helps understand its impact on homes and lives. And lastly, I'll connect the dots, how everything we found fits together and how much important they can be to our health. So we are a team of different experts like engineers, health scientists, and sociologists from FSU, Florida State University, and Harvard University. Together, we've built a big collection of information about mold growth and asthma in the aftermath of these hurricanes. How we gathered information? So we didn't do this alone. We got the help of volunteers and online surveys. We found volunteers in a few different ways. We put out ads on social media to find people interested in helping out. We also send out flyers to spread the word about our study. We teamed up with asthma health centers and communities like churches, mosques to find volunteers. And lastly, we asked our friends and colleagues to share their information and join our study. In fact, the volunteers was one of the most difficult parts of our study. With that, we gathered lots of details about various factors. We asked about general information like the names, address, gender, race, and like the number of residents. And the other information was the building properties, like their materials, roof type, home age, and so on. The next information that we got from them was the HVAC information, like AC system type, ventilation, use of humidifiers or dehumidifiers, and also people's behavior, like cleaning frequency, if they open their windows or use window blinds, how much time they spend at home, and also their smoking habits. Also, if they used professional repairs after the flooding or not. And lastly, the history of their respiratory health and medication use, asthma symptoms and attacks before and after hurricane. Frequency and also the frequency of visiting physicians during a respiratory illness. So the Harvard team visited buildings to visually inspect for mold. They were looking for damages, stains, visible mold spots, and signs of wetness from leaks or floodings. And they also used special cameras and they found areas of dampness that couldn't be seen normally. These cameras helped uncover hidden issues that might affect the buildings. They tested how well buildings' ventilation systems worked using blower door and airflow meters, and also measured airflow in exhaust fans. Samples from the air and dust helped us find out if mold was present at their homes. And the samples were sent to Orphans, which is a trusted lab. They analyzed over 40 types of mold species from the samples. This is the indoor and outdoor mold sampling results. With the results in hand, we created reports for the volunteers. These reports helped them understand the mold situation in their homes, and it was essential for the families to know more about the mold conditions in their homes, and so take necessary actions to ensure their well-beings. I used machine learning algorithms like the neural network to handcast how deep the flood were during these hurricanes at their home. So in my exploration of flood modeling, I examined different features rooted in the physical concept of flooding. This involves studying geographic elements like the proximity to rivers, storm tracks, and the coastlines. I also considered some kind of hydrological aspects such as drainage area and flow accumulation, which are crucial in understanding weather movements. The other features are like meteorological elements like rainfall depth and wind speed, which are playing important roles in my analysis. And also topographic features like elevation, land wetness significantly influence flood behavior. Surface characteristics, including imperviousness and soil moisture, provided insight into water absorption tendency. And lastly, the dynamic nature of the storm stage added complexity to the flood model. So all these features intertwined to shape my comprehension of flooding dynamics and building a flood depth neural network model, and finally have flood depth data as a result. So collectively, from our surveys, home inspections, lab results, and flood modeling, now we are looking at how all these details connect to each other and to the mold growth and people birthing problems. These analyses will help us understand how different factors are linked. So to determine the crucial factors for first, our mold growth analysis, we employ two feature selection methods: principal component analysis, PCA, and independent component analysis, which is ICA. These methods help identify the most significant features for our analysis. Based on PCA, the important features that emerged for consideration were outdoor total mold spores, if they open their window or not, ventilation system, roof type, and so on. And based on ICA, there were like the flood depths, proportion of sunlight in their homes, roof type, and again, so on. Applying the same feature selection methods, PCA and ICA, this time for the asthma, we aim to pinpoint the crucial factors. Through PCA, they identify significant features, including like the if they had some kind of professional repair or not, air conditioning system type, total mold spore inside their home, flood depths, and etc. Similarly, the ICA, there are like pre-existing asthma, days spent at home, smoking members, and so on. Finally, we conducted machine learning modeling, employing various algorithms like random forest, XGBoost, and neural network for our both mold and asthma analysis. So this result is for mold analysis, and this is Shapley additive explanations, which is SHAP, radar plot depicted the importance of factors. Excuse me. So these furthest features from the center are the most significant ones, and the ones which are near to the center are the least. So the results underscored a key contribution to mold growth, including like outdoor total mold spores, flood depths, and the building properties like the home type and material, and as well as if they open their windows, blinds or not. In our asthma analysis, based on the result of the models, this is again the SHAP radar plot revealed crucial factors. So the most influential factors impacting asthma included whether individuals open their windows or not, and the presence of smoking members at home or not, and then pre-existing respiratory disease, and also the presence of the mold spores at their homes, and at last the flood depth. This study faced several limitations. Firstly, the sample size was constrained, impacting the study's overall scope and generalizability. Additionally, the study primarily focused on medium-term impact on human health, so potentially overlooking gradual effects. Moreover, the reliability of survey questionnaires pose a limitation, potentially affecting the accuracy of collected data. And lastly, the uncertainties in flood estimations introduce potential inaccuracy in the modeling process, impacting the reliability of flood-related findings. So moving forward, this study aims to conduct actually further inside inspections on houses to expand the database and enhance understanding. And the next one is investigating a range of flood events, not solely extreme ones, to capture a more comprehensive picture. Additionally, the goal is to develop generic models to predict the indirect impacts of floods on mold presence in homes and occupants' respiratory health. Another crucial future step involves the development of practical guidelines for homeowners and building designers aimed at mitigating mold growth post-flood events. These initiatives aim to provide valuable insights and actionable recommendations for better preparedness and resilience after flood happening, and which are related to health impacts. So thank you for all listening, and I'd also want to thank all volunteers and AGU for the valuable opportunity, and my team members, including my professor, Dr. Ahmedi Sharaf, and another student, Zhengzhou from FSU, and Professor Azimi and his team from Harvard University. So I'm ready for your questions.
Fantastic. So just a reminder, if you have any questions for Miriam, please put them in the chat or just unmute yourself, and then she can answer them. So I'll start it off as people are typing or unmuting. So I think going back to early in your presentation, you mentioned for the survey, the recruitment of your participants was really difficult. Do you have anything, like looking back, Do you have any things that you would change about your recruitment strategy? Or is it just like just one of those like really hard things to just get people to get to take your survey?
Yeah, exactly. You're right. It was the most difficult part of our everything is hard, but this part was the hardest one. And because people after the flooding, they don't care about like answering questions because they lost everything, or they are not in a good situation to ask them about, so what happened, how are you feeling? So they don't answer very good, or they don't want to be a volunteer. So we did a lot. We also gave them some kind of rewards if they answer our questions, but as I said, those rewards means nothing for them, because it was a very bad situation after flooding, and they don't want to, I don't know, answer questions like that. So we tried a lot, and because it's a kind of very, I don't know, very maybe personal things, some institutions didn't help us about that. They said that it is kind of personal information. We can't give those information to you. So we are trying to get more information from different organizations, or with the help of different organizations, but up to now, that's all we have.
Got it. Thank you so much for that response.
Yeah,
So
sure.
we have one question in the chat from Charles. Who says, exciting work. Are there challenges involved with combining categorical data like rooftop and quantitative data like flood depth into a single analysis?
Actually, machine learning and stuff, that we can have both like categorical and also the numerical. The thing that I did was the categorical should be some kind of classes, like if it is yes or no, so it would be 0 or 1, for example. So the number can change, whatever the person likes can put there. But the other parts that was kind of important was that don't consider those categorical like numerical, because for numerical we have some kind of scaling, and we scale the data to be like between 0 and 1. But for categorical, because it is just category, it's not number, we put number, but this number doesn't mean that they are exactly number. So we remove them from like the scaling part, which we separated them. So for the categorical, we just consider them as category, but for the numerical, we did all those pre-processing like the scaling and the other kind of stuff.
Awesome. Thanks so much for that response. Does
Yeah.
anybody have any other questions, Miriam? You could also put them in the chat if you think of something later. All right. So thank you so much for your presentation. Exciting work. I'll echo Charles on that one. And Charles is actually our next speaker. So I will hand it over to him. You can introduce yourself and get going with your presentation. Thank you.
Hello. Fantastic previous 2 presentations. So I'm excited to be part of this. And thank you again to the people putting this together. Can everyone see my slide okay?
Looks perfect.
Okay. So hi, I'm Charles Copeland. I'm here to talk about Kawasaki disease and some of the work we're doing in environmental epidemiology to try to get closer to understanding a bit of a medical mystery. I'm a research data analyst at the Kawasaki Disease Research Center at UCSD, part of a broader Kawasaki disease climate team. So what is this disease? If you haven't heard about it before, it's a fever and a vasculitis that primarily affects infants and young children. At its worst, symptoms could include coronary artery aneurysms and lasting heart damage. It has so far an unknown cause. We believe that it starts with an immune response that depends on a genetic predisposition. But we don't know what that beginning step actually is. Currently, it's diagnosed based on a combination of symptoms, kind of an expert symptom assessment. And that diagnosis and aggressive early treatment is really important for reducing the risk of long-term damage, despite the fact that we don't actually know what the cause or the etiology is. We're very good at treating it, but early diagnosis is very important. We lack any kind of blood test, and there may be it may be underdiagnosed in some regions of the world, and there's been a major effort to sort of educate doctors on this somewhat uncommon disease. It was discovered in the 1960s by Dr. Kawasaki in Japan, and in that country it's not believed to predate World War II. Just some basic facts. So what our team is doing, we're using environmental epidemiology in search of this etiology. The cause is a mystery, along with other methods such as genetic testing of patients. One approach is to put together all the clues we have from the epidemiology and try to see how that limits sort of possible plausible etiologies. So this map on the right is sort of a famous historical map of the 1854 London cholera epidemic, where John Snow just, drew on this map where cases of cholera were occurring, and that helped nail down that the Broad Street water pump was actually a source of transmission for this cholera epidemic. So using this kind of basic facts and mapping environmental techniques to learn something about the disease. For Kawasaki disease, biological and epidemiological evidence points towards a possible aerosol agent theory. It has a quick response time, so this illness and the fever comes on really quickly, which suggests sort of exposure to an agent. Throughout the world, there are geographically specific seasonal cycles, suggestive of an environmental component. And we also see high frequency clusters of many cases in one geographic region, more often than we would expect statistically if these cases were not connected by some sort of something in the environment. We also see more low periods when much fewer people are getting Kawasaki disease than we would expect. It's kind of geographically coherent. So the presence of these clusters suggests there's some kind of common exposure in the environment. So we primarily study data from Japan for this project. We need really large numbers to prove environmental effects and to sort of sort through the noise. Japan has a large population and one of the highest rates of Kawasaki disease, which we presume is due to the genetic component of this disease. There's been extensive effort to collect hospital data on Kawasaki disease in Japan for decades, so we're very indebted to Japanese doctors and epidemiologists. And because of their careful work, we have information about more than 400,000 cases. So this figure on the right shows the rising incidence of Kawasaki disease in Japan. Going back to the 1960s, there were curious epidemic years, large spikes in the late 70s and 80s. But since then, gradually, the case rate has been increasing, which is concerning. But we have access to all of this fantastic data, which allows us to do this kind of environmental epidemiology. So I mentioned the seasonal cycle, and that's a big part of our work. This is a figure showing the average seasonality for Japan as a whole for the decade from 2010 to 2019, plotting it as kind of a fraction of the annual mean for a 14-day moving average, restricted to cases only seen in ages 3 and up, because we see the seasonal signal more coherent in some of these older kids. And what this shows, there's a peak season in winter, especially January, where in the middle of January, you have 30% more cases than the annual average, and a low season dipping in September when you see around 20% less cases than the annual average. So one thing we decided to start sorting through, we know this is the national average. Are there regional differences that could provide further clues as to what is happening with this disease? So we went ahead and tried to plot for all of the prefectures, because currently the most specific geographic information we have is at the prefecture level. This map on the right shows these prefecture divisions, so you at least get down to subsections of major metropolitan areas across the whole country. In this figure on the left, each horizontal color line is an individual prefecture for all 47. We took each prefecture's seasonal cycle and normalized it based on just the standard deviation. And plotting them all here, you can see there's this red band on the left showing that peak season, various things happening in spring and summer. And then you see in the blue, the low season, where across the country, somewhat simultaneously, you have less of this disease than you would expect. And when we first started looking at this, when I squinted a little bit, it seemed like there might possibly be a diagonal happening, where this low season perhaps starts earlier in the north of the country. I didn't mention it, but these numbers are roughly organized north to south, where Hokkaido is the top of this figure and Kyushu and Okinawa are in the bottom. But we see, possibly this seasonal feature happens earlier in the north and later in the south. So we wanted to figure out a good way to represent that and see if this is in fact a latitude gradient. So going back to this national seasonality, how we looked at this is we, for each prefecture, calculated the average date of this transition midpoint from the seasonal low to the seasonal high, which we calculated just based on the average date of the year when exiting this seasonal low period, the case rates crossed over the annual mean on its way to the seasonal high. So that's the date of this transition. So we then plotted this across latitude gradient, across the latitude for each prefecture, as well as showed it on a map. And we think we see here a very reasonably strong latitude gradient from north to south. So on the y-axis in this figure on the left, this is expressing the average date of that transition midpoint. And as you can see, Hokkaido, this date occurs months earlier than Okinawa in the far south. And in all the prefectures between these two extremes, there does seem to be, despite some noise, a decently strong latitude gradient. And in this figure on the right, you can also see this a cluster of prefectures in the north when this occurs. This transition season occurs earlier, and some noise, but in general, a gradient, especially Kyushu, this island in the southwest. You see more prefectures where this transition season occurs later in the year. So what does this tell us? For one, regionally specific timing across the latitude gradients provides further evidence that there are climate-related environmental effects. Not only is there a seasonal cycle, but this seasonal cycle depends, essentially on the local season. Winter occurs, essentially shows up earlier in the far north, and the same winter conditions arrive later in the far south. So we think this annual cycle, further evidence that this is related to the environment and not something like the school year or other sociological calendar-related effects. This also tells us that untangling environment and KD associations is going to involve untangling regional nuances. If we continue to only look at a national story and search of environmental effects, regional differences may create biases that would make possible environmental signals harder to see. So this allows us to investigate a wind hypothesis that has been thrown around for Kawasaki disease. Past studies have found evidence for relationship between Kawasaki disease and wind patterns. Epidemiological features could be explained by the long distance transport of an aerosol agent. This 2014 paper in PNAS suggested that Northeast China could be a possible source region for this supposed Kawasaki disease agent. As you know, the story that this is an immune reaction to an inhaled aerosol is also biologically plausible, as far as the opinion of the medical assessment of this disease. That still leaves a lot of possible causes. This could be a wind-blown virus, fungal spores, pollution. But the key thing we can tackle, we know that the high season in Japan correlates with this seasonal shift every year to a wind origin from Northeast China. Taking that, we want to know whether this correlation is causative, or if these are just two things that both have, correspond to the annual cycle. So this figure on the right is one of the type of things we're looking at. This is showing source air based on back trajectories of winds for 2 months for Tokyo, and it's plotting residence time. So the darker red colors and orange show more likely wind origin. Essentially what this shows is that, this region, Northeast China, lights up in January and is less likely to be a source of winds in September. We know Kawasaki disease has a seasonality, the wind has a seasonality. We would like to know whether this correlation is in fact something causative. So to explore this, we need to know, does this geographic difference in seasonal winds fit with what we now understand to be Kawasaki disease's latitude gradient in seasonality? We'd like to know whether interannual variations in wind patterns, when this seasonal pattern looks different, does that cause, or is it related to, interannual differences in Kawasaki disease? And because we have these higher frequency clusters that can be on the length of a week, do these shorter term clusters of high and low Kawasaki disease fit with higher frequency wind anomalies or deviations from seasonally expected trends? So the way we're tackling this, going further in this research, we're using HiSplit software to calculate back trajectories, and we've calculated a decade of wind back trajectories for 5 major metropolitan regions in Japan. We're going to be seeing, whether the wind in both, average and anomaly space corresponds with these features in Kawasaki disease. This is a highly multidisciplinary work. We're standing on the shoulders of giants in many ways. Involves interfacing, with the medical world, the climate worlds. So I rely on a lot of very useful collaborators. But that is my talk. I'm now open for questions.
Thank you so much, Charles. So I'll invite anyone to pop in the chat, ask your question. I can read it out loud, or just unmute yourself. Yeah, I can start for anyone who's typing or unmuting. So I know your project is multidisciplinary. You mentioned there all your collaborators. I assume they're probably from different backgrounds as well. Like someone might have an epidemiology degree. Is it, in the spirit of talking about communication, is it difficult to talk across disciplines, or as your collaborators, do you come up with like a shared sort of like language as you're tackling sort of like this one problem?
That's an excellent question. I think to some degree we have had to, the climate people have had to educate ourselves a bit on the medical things, and the medical people have had to educate a bit on the climate world. But in general, I think it does force all of us to figure out how to talk about things with more sort of general, less discipline specific language. And that's been useful, as well as because, we're kind of poking around in the dark in search of a mystery, putting together clues. So we have to be kind of open to, this may lead into a discipline that none of us necessarily have too much expertise in, or we have to be open to many possible types of science. And I think it's actually been useful to try to stay in this interdisciplinary mindset, and to be open to like different types of analysis, from epidemiology to climate science, different ways of thinking about anomalies and clusters and statistics. Yeah.
Awesome. Thanks for that. So I'll let you go.
Yeah, I have a question. So I'm
Okay.
very interested in your last slides about the high split. Can you share the slide again?
Yes, I can show that.
Can you talk more about the high split part? So what's your find, and so this is the next step, and what's your plan?
Yeah, so one of the first things was just creating kind of a decade of back trajectories. Are you familiar with high split?
Yes, I'm also a developer of high split. I'm in that group, AIL.
Oh,
So, yeah.
incredible, yeah.
But, yeah, so if you want to have more collaborations, maybe we can, you can send me an email. Yeah.
Oh, fantastic. Yeah, but to start, we're not the first people to use back trajectories to look at Kawasaki disease, this possible wind hypothesis. But I think what we realized we need to do is really think about dealing with this tricky problem of seasonal anomalies to try to get to, whether this is a causative correlation. So a lot of that has been like this figure, high split creates individual particle back trajectories, primarily use like the dispersion model. Been figuring out ways using variables like residence time to combine, hours, days, a long span of multiple dates of back trajectories to create, to try to calculate something like what is a seasonal average, what does the average January look like, and then how does, a particular set of dates, how do we think of anomalies from what we'd seasonally expect? And one thing you can do is using something like residence time. Another thing we've been exploring is taking those back trajectories and trying to figure out, just trying to condense this sort of complicated information into something like just like what is the average wind direction origin from the preceding 6 hours? What is the average distance that which is from the preceding 6 hours, which is a nice proxy for wind speed, and other ways of thinking about how do we, if we wanted to if we wanted to pick a particular season and wanted to group wind into different categories, what are different metrics we can use to sort of cluster wind into a top 5 possible wind patterns you'd likely to see in January, and then see how those frequencies change year to year. Yeah, but several different techniques essentially.
Okay, thank you.
Yeah.
Awesome. So I think we're coming right up on the hour. I want to thank you, Miriam, Charles, for your awesome presentations, and also sharing with the world again your awesome research. I think it's awesome that there were some synergies, high split, but all like really interesting, showcasing what's possible in geohealth. So thank you all, and have a great day.